In this video, we will look at the operation for BJT with the transport model for a BJT, the equations related to the transport model, regions of operation, and later on we'll look at an example problem. Okay. So let's switch to the class notebook. So here we have a illustration of a BJT. As a recap, construction of a BJT is unique. It is not a symmetrical device. We have three regions: collector, base, and emitter. And the doping for all three of them are different. The emitter is the most heavily doped, followed by the base, and then last is the collector, which is the least heavily doped. Okay, so here we have the emitter on the left, base, and the collector on the right. This illustration is showing a NPN transistor, NPN. And as stated previously, the N plus and the N plus plus is simply relative. It's showing that the emitter is more heavily doped as compared to the collector. Okay. The base doping is somewhere in between, but it is a very thin layer. It's a physically very thin layer. So this obviously is not to scale. Okay. This is not to scale. This region is very thin compared to the emitter and the collector. Okay, so here we can see the emitter and base is applied a voltage VBE. Collector and base is applied a voltage called VCB. And we can see that the emitter base junction right here, it's a PN junction diode, it is forward bias. Okay, the N-type region is connected to the negative end of the voltage source. And at the same time, the collector region is reverse bias. Right there, we have an N-type region that is connected to the positive end of the source. So this is forward bias and this is reverse bias. Now, what this does is, well, the base emitter region behaves like a PN junction diode. You have the majority carriers of electrons that cross over to the right and they go into the base region. Now, when they reach the base region, you will expect recombination to take place, meaning the electrons that are crossing over will recombine with the holes that are present in the p-type material. But here's where the funny thing happens. It is a very thin region and there are not enough holes to combine with the flood of electrons that is taking place in the base region. So there is some amount of recombination that takes place. However, it is a small fraction of the total number of electrons that are present in the emitter. And so a small current at the base will flow through, that is indicated by this current IB. It's a very small current, typically on the order of microamps. But a majority of the electrons are able to cross over and pass through the very thin P layer, which is the base layer. Now, this is ensured during the design and the manufacturing process. Okay. The diffusion of the electrons in one direction, of course, is also accompanied by the diffusion of holes in the opposite direction. So that also contributes to the total current flowing through the emitter. Okay. A majority of the electrons, however, pass through the base region and cross over into the collector region. And that by far is the reason for the collector current, IC being very, very close in value to IE. Okay. So even though the collector base junction is reverse bias, we have heavy current flow due to the unique fabrication of the BJT. Now, we look at the transport model. This is the basic operation of a transistor, of a BJT transistor. Let's look at the transport model, and then we can look at the equations governing that model. Okay. Some of the BJT parameters to look at is the ratio of the currents, IC to IE and IC to IB. The ratio of the collector current to the base current is a very important parameter of a BJT. It is termed as the beta. It is the forward gain, the forward current gain for a BJT. So this is known as the forward current gain of the BJT. Okay. Alpha is the ratio of the collector current to the emitter current, and would approximately equal 0.99. So typical values for alpha would be about 0.99, considering that the emitter current is the sum of the collector and the base current. Okay, the base current, as I stated earlier, is typically on the order of microamps. All right, so now let's look at the transport model. Okay, in this transport model, we're looking at a NPN transistor. And of course, this NPN transistor can be referred to as two diodes, right? Connected back to back with a common P region. Now, the narrow width of this base region enables the coupling of these two diodes. And we already saw the emitter injects the electrons into the base, thus causing current flow. And current flow, of course, is always taken in the opposite direction of the flow of electrons. So if electrons are flowing in this direction, current IE is flowing in this direction. And again, as a reminder, current flow in a BJT takes place due to both holes as well as electrons, hence the name bipolar junction transistor. Okay, the base emitter voltage VBE and VBC, the collector base voltage, determine the currents in the transistor. Now, if both respective PN junctions for the base collector and the base emitter are forward bias, then we say both currents are positive. Okay, so as shown here, VBC and VBE are indeed forward biasing both PN junctions. So IC, IE are all termed as positive. So the terminal currents in this BJT are respectively IC for the collector current, IB for the base, and IE for the emitter current. Now, recall that for a JFET or a MOSFET, the gate is electrically isolated from the transistor structure, the substrate. Hence, in a FET or a MOSFET, the gate current IG is practically zero. However, here for a BJT, the base actually has some value and typically it's in the order of microamps. Okay, typically on the order of microamps. So let's see, we'll define both forward as well as reverse characteristics based on the power supplies that are connected. So in the forward characteristics, VBE is applied to the base and emitter, which forward biases the base emitter junction. And we are shorting the collector and the base. And so VCB is equal to 0. So VCB or VBC, if you will, is equal to 0. So the forward transport current can be described in terms of the collector current. Okay, and in this case right here, IF can be described directly by the diode equation. So we can write IC is the forward transport current, and we can write IC is equal to the saturation current, IS, E raised to VBE divided by the thermal voltage, VT. Hopefully that rings a bell from chapter 3 for the diodes. Okay. And again, IS is the saturation current for a normal reverse bias PN junction. Saturation current. Okay. And VT, of course, is the thermal voltage. Can take VT as 25 millivolts, 25.8 millivolts. Typically our book, the textbook uses 25 millivolts. And so for the rest of this class, of this course, we will stick with 25 millivolts, so there's no misalignment with the text. Okay. So the saturation current, of course, is in nanoamperes or less. And we can also write an equation for the base current as IB is equal to IS divided by beta F, then E raised to VBE over VT minus 1. Now, beta we already described is the current gain, and here beta F is the current gain, but is the forward common emitter current gain. Okay, current gain. All right. And then finally, we can write emitter current IE. IE is the sum of IC plus IB. Okay, IC plus IB. Okay. So those are the forward characteristics for a NPN transistor. Now let's look at the reverse characteristics. In the reverse characteristics, we see that now the base emitter junction is shorted together. So VBE is equal to 0. And we are applying a voltage across the collector and base junction known as VBC. So when we apply a voltage, current's going to flow through, and we now call this current as the reverse transport current IR, okay, flowing through the collector. It enters the emitter, goes through the base region, and then out of the collector terminal. So we can write an equation for the reverse transport current, and then in the reverse transport current, we can write it in terms of IE. So we can write IE. Remember, it's an NPN transistor. IE is taken as flowing out of the transistor. And so IE is opposite of the reverse transport current, so minus IR. It's the same standard equation. We can write IE using the standard diode equation, and you can write it as IS to E raised to VBC or VT minus 1. Okay, and from IE we can write IB, and IB, the base current can be written as the reverse current, or basically IE. So IS or beta R, and E raised to VBC over VT minus 1. Now, beta R is the reverse common emitter current gain. So beta R is the reverse common emitter current gain. Okay. And finally, of course, we can write IC is equal to IB minus IE. Okay. We can write equations for the complete transport model. And so if we combine the equations, we can write an expression for the collector, emitter, and the base current, irrespective of any biasing conditions. So I can write IC is equal to IS times E raised to VBE over VT minus 1. And this rearrangement of terms, oh, actually not minus 1, minus E raised to VBC over VT. And this would be minus IS over the reverse current gain, beta R, E raised to VBC over VT minus 1. Similarly, we can write IE is equal to IS times E raised to VBE over VT minus E raised to VBC over VT, and this time plus IS over beta R E raised to VBE over VT minus 1. And then finally, base current IB is equal to IS over the forward current gain beta F and E raised to VBE or VT minus 1, and then minus IS or beta R or VBC or VT minus 1. Okay, so these are combining both the forward and the reverse, and we have the complete transport model, and the equations describing the complete transport model for a BJT. At this point, I would definitely assign a reading from the textbook. So it's a lot of explanation then that is available in the book, then can be covered in a simple lecture or a small lecture. Okay, so now that we have a transport model, let's look at an example. The example is rather straightforward. We are given a circuit BJT with biasing voltages, and we are asked to find the terminal currents. So IC, IE, and IB are required to be found. Okay, so what do we need? Well, go back to our equations. We need IS, which is already given to us. We need voltages for VBE, VT, VBC, and of course, the beta. So what else is given to us? Oh, let's see. Beta F is given as 50. Beta R is given as 1. Okay. And IS, the saturation current, is given as 10 raised to minus 16 amps. All right. So let's go ahead and begin our analysis. This is rather straightforward. Okay, we have the equations. All we have to do is extract all the information that is possible from the circuit diagram and then plug it into the equations. These are the values that are already given. Okay, these values are already given as part of the problem. Okay, so we need VBE and we need VBC. We don't have those, but we can easily calculate. If we apply KVL in the input side, we can see there are only two voltages. VBE is equal to VBB, or 0.75 volts. VBC is connected between VCC here and VBB here. Positive reference is at the base, negative is at the collector. So it's the difference of the two voltages. In this case, since positive is VBB, it would be VBB minus VCC, gives me minus 4.25 volts. Thermal voltage is not given, but we can assume VT is 0.25 volts. I'm sorry, 0.025. You can also use 25.8 millivolts, unless the problem states specifically 25 millivolts. Since it's not given, we'll assume 25 just to stay consistent with the text. You have all the values now. Plug into equations and solve. I will tell you the values. IE is 1.071 milliamps. IC is 1.07. IE is 1.09. Has to be close, right? IE is almost equal to IC, or I should say IC is almost equal to IE. And then of course IB is 21.4 microamps. IC plus IB should give us IE. Okay. All right. That's the transport model. A PNP BJT. Oh, let's go back. A PNP BJT would behave exactly the same way as the NPN BJT, except that everything is reversed, meaning electrons are replaced by holes and holes are replaced by electrons. Everything else remains the same. The current flow changes. The emitter current is no longer coming out, it's actually going in to the BJT. The collector current also is not going in, it's coming out of the BJT. All other conditions remain exactly the same. Okay, so PNP BJT transistor behaves exactly the same as an NPN BJT transistor. Okay. So when we are analyzing nonlinear devices like diodes and BJTs, we always like to use different models. Remember, one model does not completely describe one single device. We always need multiple models to describe the behavior under multiple conditions. The transport model of the BJT is very useful, and the equivalent circuit representation can be given by these figures right here. Two back-to-back diodes. In case of an NPN transistor, the anodes are connected together. A PNP transistor, the cathodes are connected together, and in parallel with a current source. The current source, of course, supplies constant current. That would be the forward current. And so, constant current source, and it's a dependent source. The dependency is on VBE. So constant current source, or it's controlled by VBE or IB, the base emitter voltage or the base current. Okay, so anytime you're working with circuits, these equivalent circuits are very useful in describing the transport model. Now, based on the biasing conditions, there are 4 operating modes of a BJT that are listed right here. So we have 2 junctions, and both junctions can be either forward bias or reverse bias. So if you have the emitter base junction as forward bias and the collector base junction as reverse bias, we refer to that as the forward active mode. The forward active mode. And this forward active mode is by far the most popular for use as analog amplifiers. In the forward active region, the BJT behaves as a very good amplifier. Okay, a small amount of input current at the base can result in a very large output current at the collector. And then if the junctions are both reverse bias, we say that the transistors are operating in cutoff. If both junctions are forward bias, we say transistor is operating in saturation. And these 2 modes used together in a circuit allow us to create digital logic circuits using a transistor, a BJT transistor. In a saturation region, we say that the transistor is conducting fully open, and so we can say it is similar to a closed switch. A closed switch that allows uninterrupted and unimpeded current flow. In the cutoff region, as the name suggests, BJT is cut off. There is no or very minimal current flow, and we can refer to it as an open switch. The closed switch and the open switch together, together allow us to create digital logic or binary logic circuits. Okay, closed switch would be 1, open switch would be 0. So these are the three main regions. The fourth one, however, where the emitter-based junction is reverse bias and the collector-based junction is forward bias, is prohibited, and it's marked in red. It's a reverse active region, and the reason it would not work in such conditions is, of course, because of the asymmetrical nature of the BJT construction. Okay, the asymmetrical nature. So these are the three primary modes of operation: the forward active, the saturation, and the cutoff. Okay, I think for this video we'll stop right here, and then we'll pick up from this point on in the next video, next lecture.